Hello, in this video we are going to cover mean and standard deviation. So as explained in a previous video, the study of data includes finding the typical value or the center of the data and the variation or the spread. So we want to go through and we want to find the typical value, the center. We want to find the variation or the spread. Why do we want to go through and find those things? They're just classic questions. Frequently, it's when you're going through and you're studying data, it's something that you're interested in. For example, if you were studying the height of women, one of the things that you would be interested in would be what's the typical woman's height? What's the middle woman's height? What's the most? If you selected a woman at random, most likely what height would you end up with? And then after you went through and answered that question, your next question would be, okay, well, how do the heights of women spread out from the center? Do they spread out rapidly or very gradually? So, that's another question. And the reason you'd ask that would be to try and identify, what's an unusual height for a woman? So those are the types of questions that you ask when you look at data. You're interested in what's typical, and then how does the data spread out. So we're gonna try and look into methods for answering those questions in this video. In particular, we're going to look at. So this video is on popular methods for answering those. We're going to look at the mean is for finding typical value. Or the center, and then the standard deviation. Is for finding variation or the spread. Okay, so let's start off with the mean. We'll start off on a new page here. So the mean is the idea of defining the typical value / center of the data as the balancing point. Of the distribution. So we'll make that a little bit clearer. What do we mean by balancing point in just a minute? But just to finish off, that's our definition here for mean. It's calculated by finding the arithmetic average. Okay, so let's spend a few minutes talking about the balancing point idea, because it's an important element of what a mean means. What does it mean to go through and find a mean? That's finding the balancing point is an important part of that, understanding that. So let's go through and take a look at some pictures here to try and help us to kind of grasp what that means. Okay, so here we have a distribution. This is a dot plot. So we've gone through and we put, um, we've gone through and we've collected data on ACT scores for statistics students. And then we went through and put a dot for each score, that was in the data in the distribution. So if you count these, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Looks like maybe 10 students had a score of 22. Okay, so visually, you look at this data. Now imagine the idea of going through and let's say that we had a piece of wood, like a lengthy piece of wood, and we went through and we put weights on that wood, and we put 10 weights at 22, 2 weights at 30. We put a number of weights, and we went through and we spread these out so that they're equal distance apart. So let's say maybe you had 18, and then you want a foot, and you put a weight at 19, and then you want a foot, and you put I don't know how many is that. That looks like 6 weights at 20. So you went through and you took this long length of wood, 2x4, and then you went through and you put weights on it. And then what you wanted to do is you wanted to go through and find the place where if you put a you held up the piece of wood just with one point, just a single point, you found the place where that single point where that piece of wood would balance, right? So it wouldn't fall to the left, which is over here. It wouldn't fall to the right. It would just be perfectly balanced. Okay, that balancing point, that is the mean. Okay, so that's the idea behind the mean, is to find the point where you'd go through and you would balance the distribution. And so in this case, that point has already been found, and it's labeled here with this small little triangle. The term that they use here is the fulcrum. So I think that's a technical term for the balancing point, is the fulcrum. And then the other way to think about it is if you think in terms of a seesaw or a teeter-totter, it's the point where you'd have the two sides in equilibrium, so that doesn't fall over. And so that's the idea of the balancing point. And so in the previous definition, we said when you go through and calculate the mean, you find the arithmetic average. The arithmetic average gives you that point. It gives you the balancing point. At this point, though, like that's kind of, we're going to do the calculation in a few minutes, but what we want to do is just make sure that idea is clear. And the goal is that you could go through and look at this distribution, see it without the little triangle there, and be able to eyeball roughly where the balancing point would be, roughly where the mean is. So you do want to have that skill where you could look at this and say, you know what, where's the point where it looks like we have, weights on the left, weights on the right, and weights on the left, and they're roughly in balance. And in this case, the triangle is already there, so it's not like you can unsee it. But hopefully, if you just imagine it not being there, you'd guess somewhere in this vicinity would be the point where you'd go through and you'd find balance. Okay, so and in particular, this point is at 24.6. And that is the mean. Okay, let's look at another distribution. Okay, so this time we don't have the fulcrum on there. We don't have the little triangle. The mean is not labeled. And again, the idea is what we want to do is we just want to practice identifying the mean without going through and doing the calculation, just by looking at the distribution. And it's not going to be perfect. The whole point of this is to try and approximate it, to try and make a guess at roughly where it would be. And so if you look at this data, roughly where do you think it would be? Just kind of visualize it, and then, we'll make a guess. Okay, so I'm taking a look here. I see, you got this long bar here. It's longer than this one, so that makes it seem like this side would maybe have a little bit more weight on it. But then the next bar, this one is bigger than that one, and you've got more stuff here on this side, more stuff on the left here, that's further down than here on the right. And so it looks like maybe any less weight, if you want to think about this like on the weight and on the idea of a teeter-totter and balancing this, any deficiency in weight from this bar compared to this one, it looks like it's more than made up for by these others. And so just eyeballing it, to me, it looks like it's really probably, obviously it looks like it's somewhere in this middle bar between we've got 450 and 500, and it looks like it's pretty close to the center. So I'm going to guess that it would be around 475. And that's just a guess. And we're just guessing, we're guessing the balancing point, but the balancing point is also the mean. So we're guessing the mean. Okay, so one thing that made that guess relatively easy was the fact that the shape of the distribution here. So you'll notice that it's unimodal, like, so there's only one peak, and that it's roughly symmetric, right? So it's not perfectly symmetric, that it's roughly symmetric. All right, and it turns out that those are actually important qualities to going through and being able to use the mean as the typical value, is that you need to have a distribution that is unimodal and symmetric. If it's not, then you can still go through and calculate the mean and you'll get a value for it, but that value might not be representative of the typical value, the center of the data. So let's take a look at that just to kind of illustrate that and wrap our heads around it. So here's another distribution. This time we have winnings in the 2018 season of the top 100 ranked tennis players. All right, so they've gone through and they've plotted them. This is a histogram. And they've also gone through and put the mean on the picture. So we're not going to be able to guess because it's already there. However, if you look at that value, does that value, where that little arrow is, that little triangle is, does that seem like the typical value that's in the distribution, right? Does that seem like the center of the distribution would be there? And this is just a thought experiment. So if you're thinking, yes, of course, or no, that's a terrible idea. Let me give you a little bit more information that might help you, determine for yourself whether that seems like a good spot for a typical value. If you were to draw a line right there, see if I can get this to work. All right, it's a little off, but I think I can move it. Yep. All right, so if I put that line there, and I went through and compared the amount of data, the number of entries, the number of players, right? We've got 100 players, the number of players that are to the left of that line and the number of players that are to the right of that line. 75% of the players are over here. 75% of the results are here on to the left of that line. So does that seem like a good spot for the typical value if 75% of the players are to one side of it? The answer is no. If you think back to the example we did earlier with heights of women, if we went through and picked a value for the typical value, that the center of the distribution for women, and 75% of women were to one side of it and 25% of the other, the response would be like, well, that wasn't a great choice for the typical value. That's probably not actually the center of the data if 75% are to one side. Okay, and so what went wrong here? Why did the mean do such a poor job of determining the typical value or the center? Well, there's a couple things that are wrong here. So first of all, the data is not symmetric. So, I mean, I just said in the last thing that the symmetric data is really what you need. But the issue is that you have a few really high earners that are far, far off to one side. the whole point of this is to balance like a teeter-totter. And the further off you have these really big high values, the more entries you need to the left of this line to offset it. Okay, so these couple entries over here that made a ton of money, are Roger Federer's, and is it Rafael Nadal? I think. Anyway, I'm sorry if I got that wrong, but anyway, they got a couple people who made a lot of money. That pulls this bar to the right, and so we need to have a ton of players that made very small amounts to go through and just scale-wise, weight-wise on our teeter-totter to offset these big earners. And so it's just an example of how the mean fails when you have data that is distributed in that way, that is, that's not symmetric, right? Where you have a long right tail, that long right tail ends up, pulling that data to the right, and in pulling that data to the right, it ends up causing this situation where 75% of the results are off to one side. Okay, and so this example again, so just one more, one more way of saying it. So this would not do a good job of identifying the typical value. If 75% of the entries are on one side of the mean, then that tells us that the mean did not do a good job at identifying the center. Most likely your data is not symmetric, and it was a mistake to go through and use the mean to find the typical value. When this happens, when we have a distribution like this that's not symmetric, we will go to an alternative method for finding the typical value. We won't use the mean. So this is just an example where the mean does not work well. And in particular, it did not work well for finding the typical value. I mean, in terms of calculating the mean, there's nothing wrong with calculating it. It just is not of particular. It's not really of use. Okay, so let's go through and write that down. Write that the result that we just came to. Let's go through and write that down, and then we'll get into actually calculating the mean. Okay, so the result we just got is that the mean is useful for finding the typical value center when we have unimodal, meaning one peak, and symmetric. Okay, so now that we've kind of written that down, we know when to use it. Let's actually get into calculating the mean. All right, so calculating the arithmetic average. Which is the mean. Oops. Sorry about that. Do that first. Okay, so there's some symbols up here. So the mean, this is the symbol that we use for the mean. It's an X with a bar over it. So when you see X with a bar over it, that means the mean. The N here, this is the number of observations in our data. X stands for the observations themselves. And then this weird kind of squiggly looking E is called a sigma. And it stands for sum. So in English, if you were to write this down, this is saying to sum the observations and then divide by the number of observations. So we want to add all the observations. Then divide by the number of observations. Okay, let's go through and do an example. All right, so what we've got here that's not labeled, but what this data is it's gas prices. This is not very current. I didn't write it down here, but this is, I think this data was from, I don't remember. I think it was from like 5 years ago or something. But yes, it's certainly not very current. But this was gas prices at gas stations in some region. I think it was in Texas. Anyway, I didn't write all that down, but it doesn't really matter. While the context is interesting and it's important, we can go through and calculate the mean just by having a bunch of numbers. All right, so we want to go through and do this. So the mean, which is X bar, what you want to do is you want to add up all the observations and divide by the number of observations. So we want to go through and do 2.19 plus 2.19 plus 2.39 plus 2.19 plus 2.24 plus 2.39 plus 2.27 plus 2.29, 2.17, 2.29, 2.30, 2.29. I can do that right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I believe there are 12. So I think we've got that right. You want to add all those up and then divide by the number of observations. So how many are there? I just said it. So there's 12. Okay. And so at this point, you can break out a handy calculator to go through and figure that out. I will go through and do that. Just one moment. Okay, I went through and paused the recording and went through and did that. Assuming I did it correctly, I got 27.2 and then divide by 12. And so if we do that, we get 2.26 and then repeating. We'll round that up, 2.27. Okay, and so that's how you go through and calculate a mean. That's all there is to it. You just take all the data, add it up, and then divide by the number of observations. So let's quickly take a look at how to do this using StatCrunch. It's really easy. One second, it takes a minute for me to find the correct window. All right, so all I did here in StatCrunch was just go through and take the data and just enter it into a single column like this, 2.19, 2.19, 2.39, and so on. Once you have the data entered into a column like this, to go through and calculate the mean, you just go over, click on stat, click on summary stats. That's where it is, on summary stats. Click on columns. All right, so because we're doing columns, so it looks like you could also do a mean for a row, but we're doing a column here because that's how I entered the data. Click on column. Where is the column that you want to calculate the mean? Select that. There's a bunch of different options here, so you could go through and find more than the mean, or you could just find the mean. Let's just go through and highlight all these just for fun. Yeah, we don't need to play around with any of this other stuff. Hit compute. And if we hit compute, what do we got here? So we've got it went through and calculated a bunch of stuff. What we're interested in right now is we're interested in the mean, because that's what we just went through and did by hand. And look at that, 2.26 repeating. All right, and so that's just a real quick way to go through and calculate the mean using StatCrunch, is that once the data is in a column, you can just select stat. So let's go through it one more time. So actually, let me delete this so that it's not sitting there. All right. I can't seem to delete it, but yeah, anyway, click stat, summary stats. There we go. Columns, variable 1, you can just leave that, compute. And also, so these other things are things that we'll talk about later, but you can see that it's got n, which is which as I said was the number of observations, and then we're going to talk about variance and standard deviation a little bit later, and then in another section we'll talk about median and range and quartiles and such, but not in this video. So we're just focusing on mean for right now. And that's it. So that's how you go through and use StatCrunch to calculate the mean. Okay, I'm just checking my notes here, and I actually had one more picture that we could look at for mean, and then we're going to move on to standard deviation. So that additional picture. Where is it? Here it is. So what we've got here is we have another distribution. So this is a histogram. This represents the amount of particulate matter for 371 US cities. And the idea is, again, what you want to be able to do is to take a look at this and make a reasonable guess as far as where you think the balancing point would be. That is a desired skill, is that you could tell that without actually doing the calculations. Now, you don't need to be super accurate. It's enough to just say, you know what, it's somewhere here in the middle. And so if you kind of think about the balancing point, you've got these two tall bars. When you've got two tall bars in the middle, usually the balancing point is going to be somewhere between the two. So you can kind of think about, off to the left here, but off of these two. This one is a little taller than that one. And so you'd think maybe it's going to lean a little bit to the left and be inside, this taller bar, but then hold on, you've got a tail, you've got a bunch of data over here that's going to pull that data back to the right. And so while this is taller than that one, and actually of the two in the middle, this one is taller as well. Both of those are pulling us to the left in terms of just putting weights onto a teeter-totter. These outliers, not outliers, but well, some of these are probably outliers, but the tail on here on the right hand side is going to pull that back to the right. And so, glancing at this, I might even guessed that it's even to the right of, that's even in this on the right side of our two tall bars in the center. So my guess might have been, somewhere around right here, just as an eyeball. But if you go through and check this, according to this, 8 is actually, so it's right in the middle, according to this. I don't know whether that's accurate or not. But one of the things that one of the reasons I wanted to show you this, other than it's just another balancing point thing, is I wanted to show you how many pieces of data that we had in this collection. There are 371. And so what we just did with StatCrunch, where we went through and used computer software to calculate the mean, when you get into a lot of data, you're not going to be going through and adding up all of the data by hand. I mean, it's just not realistic. So 371 US cities, even that could be a small data set. You could have data sets with thousands of pieces of data in them. And so you do want to have a tool for going through and calculating the mean when that happens. And that tool is going to be software. So in this class, we're going to use StatCrunch. You could also use Excel. There's a lot of different options. Okay. So anyway, I just wanted to show you that. And now we can move on with standard deviation. All right. So standard deviation. What is the standard deviation? It is a measure of how far observations are from the center. So when you have a data set that has entries that are very far from the center, it's going to have a large standard deviation. And when you have entries that are very close to the center, it's going to have a small. So large standard deviation. You have lots of entries far from the center. And that center is calculated using the mean from the center / mean. And a small standard deviation has few entries far from the mean. So let's look at an example to kind of wrap our heads around what that means. All right, so what do we got here? So we've got data. This is for 2 US cities. One of them is San Francisco. So this is over the course of a year. The other one is Provo. All right, and so what we're doing is we're looking at the just a histogram of how many days are in each temperature range. Okay, so when you look at this, you can see that in Provo, you've got entries that are down here in the 40s, even 30s. In San Francisco, you don't. In Provo, you also have a big bar for 90s. You've got a lot of entries in the 90s. In San Francisco, you don't. All right. And so the difference between these, oh, and one other thing I should make clear about this, you look at and you might not be able to tell this at a glance, but if you were to try and find the balancing point, if you were to try and find the mean, right, it looks like it's maybe somewhere on this distribution, maybe somewhere in this middle bar. And then over here in this one, the balancing point, if you put these weights onto, these tall guys in the 90s, those are going to pull it to the right. I don't know. I'm going to guess maybe somewhere around here. Okay. And if you actually look it up, the mean for San Francisco, hold on. Is 65. And the mean for Provo is 67. So the means are almost exactly the same. And yet, if you look at the distributions, they're very different. What is the difference between these? And if you were to go through and just describe them to somebody, you would say that the data in San Francisco, that the average high in San Francisco, the max temperature, has a fairly narrow range. That's an attribute of San Francisco, is that it doesn't, you don't get very many really cold days, and you don't get very many really hot days. San Francisco the temperature is very consistent. Meanwhile, Provo is exactly the opposite. You have a lot of very cold days, a lot of very hot days. There's a lot of entries that are far from 67. Okay, and so here, if you were to describe this, you'd say there's a lot of variation. Or visually, you might look at this and say, you know what? The data is really spread out. And here you'd say very little small variation. Or that, the data is not very spread out, it's very concentrated. And so this illustrates the difference for standard deviation. This would have I'm running out of space here. This has a high standard deviation. This has a low standard deviation. And so we could see visually the difference between those. And we are interested in being able to quantify that, describe that with a number to somebody. And so that's where our actual calculation of standard deviation is going to come in. We're going to have a formula for it, just like we have one for the mean. But the first goal is to just understand what it means to have a high standard deviation versus a low one. High standard deviation, that means there's lots of variation in the data. The data is really spread out, right? The whole point of standard deviation is to go through and try and define that spread/variation, question that we said was of interest when you're going through and studying data. And so you can see when we have lots of variation, lots of spread, that goes with a high standard deviation. Small variation, not lots of spread, very concentrated. That's our low standard deviation. Okay, let's take a look at another picture here to try and continue to help us evolve our understanding. So we have three just sample distributions here. Again, we're just kind of working on our understanding of what a standard deviation is before we get into the formula. And the question is, which would have the highest standard deviation and which would have the lowest? When you're thinking about that question, what you want to think about is which has the largest number of entries from the center. That's a high standard deviation, is when you have entries far from the center. Then which has the most concentrated number of entries at the center. That's going to have the smallest. All right, so lots of entries far from the center. That's a high standard deviation. That's a high spread. That means there's a lot of variation in the data. Very few entries far from the center. That's small spread, small variation, small standard deviation. Okay, so with that in mind, let's go through and take a look. So which one of these is going to have the smallest standard deviation? It's going to be this one. This has the most data at the center, the most number of observations in the data that are close to the center, right? So if you were to go through and look at this, so just kind of comparing these, the bar here at the center, 4. And the average, I think, in all these is like maybe 4 or 3.5 or something. They didn't give that, but I'm just kind of, well, maybe more like 4, maybe a little bit over 4 actually, because we've got this big bar that's taller than that one. Anyway, that's not the point. I just was going to use that to illustrate, and that is that right here in the center, we have 325 entries. Look here, if this is the center of this, you only have 175. And then over here near the center, you only have like 100 entries. So you have far more entries that are near the center of this data than either of the other two. And so this one is the most concentrated, the most number of entries near the center. And so this is going to have the smallest standard deviation. All right, and then if we go through the other two, just kind of go to the opposite extreme. Here, you've got these the 250 entries that are at 1, 250 entries that are at 6. You've got a lot of entries here that are far from the center, much more than over here, right? So how many entries do we have that are far from the center here? The 1 only has about 175, the 6 about 175, and so 250 at 1 and 6 here versus 175 at 1 and 6 here. There's way more entries that are far from the center. And so this would be kind of what the, a distribution that you could hypothetically have where you'd have a very large standard deviation. And then this is the one that's in the middle. Okay, so with that in mind, let's get into calculating standard deviations now that we've kind of got our idea behind what they are. Let's see if I can find. All right, so let's go back to our gas price example. Oh, whoops, actually, sorry, I need to write the formula down first. Just kind of skipped ahead there. All right, so the formula for calculating a standard deviation. The letter that we use is the letter S. It kind of looks like a 5, but my S's often look like 5s. So that's supposed to be an S. All right, and what it is it's the square root of the sum x minus x bar squared divided by n minus 1. All right, so we've gone through and we've defined what all these symbols are, I guess, except for the S. But so the X is still going to be the observations. The X bar here is still the mean. The N is still the number of observations. And this is the squiggly E here is still sigma or sum. All right, so what are we doing here? What you're doing is you're taking each observation, you're subtracting it from the mean. When you do that, when you take an observation and subtract it from the mean, that gets you the distance that that observation is from the mean. So you're finding the distance from the mean, then squaring it. Why square it? Because that makes it positive. Could there have been a formula like this where you had absolute values? There could have been, but that's not what the formula is. And so what we want to do is we want to have all of our measures of how far the observations are from the mean. We want them all to be positive. So that's why we take an observation, subtract it from the mean. That gets us how far that observation is from the mean. We square it to get it to be positive, and then we add all of those up. So we're doing here sigma, add all those up, divide by n minus 1, and then we take the square root here. And the square root at the end is really to offset this square, and so you end up with so you don't end up with squared units. And so this is a little bit complicated, but if you were to go through and take an observation and subtract the mean and then square it, if there are units for whatever thing you're working at, like so if you had like the particulate matter problem, you've got the observation is going to be a number of particulates, the mean is going to be a number of particulates. If you subtract them, you're going to get the difference is going to be a number of the distance is going to be how many particulates you are from the mean. If you then square, you're going to have squared particulates. And so at the end, we square root to make it so that we don't have squared units. Okay, why are we dividing by n minus 1 instead of n? That's a question that we are going to come back to in a later section. Okay, so anyway, that's the idea. I'll go through it one more time if there's probably people who are just like, it's just blah, 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 blah. But what you're doing here is you're taking an observation, you're subtracting the mean to measure how far that observation is from the mean. You're then squaring that to make it so that it's positive. You're adding all those distances from the mean squared. You're adding all those up, and then you're dividing by the number of observations and square rooting to get rid of the squared unit at the end. Okay, so that's our definition for the standard deviation. Let's go through, and I'm not sure I'm going to do all the calculations because I don't know that it's going to fit, but let's just at least get our calculations started for our gas prices. Okay, so we have our picture here. So we want to go through and find what the standard deviation is of our gas prices. So we know what the mean is. I believe it was 2.67. We estimated it as 2.6. It was 2.6 repeated. No, that can't be right. All right, what was it? Hold on. Let's go back and look because I have no memory for these kinds of things. It was 2.27. All right, there we go. 2.27. Let's jump back. 2.27. All right, so that's the mean. That's the center. The first thing that we want to do is find out how far each one of these entries is from that. And the way that you do that is you subtract. So we're going to take 2.19. That's an observation. We're going to subtract the mean. That'll tell us how far we are away. This is something we could just do this in our head. So what's 2.19 minus 2.27? It's 8 cents away. So we're going to get 0.08 for the first one. See if I can get this to fit. And that is a negative 0.08, right? Because this minus, the mean is larger, but we are going to square these observations to make it, square these distances to make them all positive. 2.19 minus 2.27, you're going to get another negative 0.08. 2.39 minus 2.27, that's what, 12 cents? That's a positive 12 cents. And then another negative 0.08. 2.24 minus 2. That's 0.03. Negative. We got another 0.12, 12 cents. That's a zero distance. That's okay. 2.29 minus 2.27. That's going to be a positive 2 cents. Then we've got negative 10 cents. And then we've got 2 cents, 13 cents, and then 2 cents. All right, so what we did just there is we went through and we found out how far each one of our observations is from the mean. Once you do that, the next step is we want all these to be positive. To get them all to be positive, we're going to go through and we're going to square all of them. All right. Hold on, am I really going to do this? Let's see. We'll square some of them maybe. All right, so so you take 0.08 and you square it, you get 0.0064. All right, and then you can do the same thing to this one, 0.0064. 12 squared, or 0.12 squared. That's going to be 0.0144. All right, and you can go through and do the rest of these. So you're going to square all of these different entries until we get to this. What's this? 0.02. That's going to be 0.0004. All right, so you want to square all of them. And then when you're done squaring all of them, so now we've got all these positive values that represent, the distance that an observation is from the mean squared. The next you want to go through and add all them up. You want to add these. So we'll put a little summation symbol. All right, I'm going to pause it and I'll go through and I'll do this separately so that we can, just to speed things up here. All right, so I went through and did a bunch of math here, took all these, I went through and I squared all these, added them all up, and this is what I got, assuming I didn't make any mistakes. I got 0.077. Once you've done that, right, so if you go look back at the formula, it's the sum of the difference between the observation and the mean squared, and then you want to divide by the number of observations. All right, so we would, after we do that, we want to do 0.077. Sorry, the number of observations minus 1. So we want to take, there's 12, we want to divide by 11. And if you do that, you're going to get 0.007 is what I wrote down. Okay, yeah. All right, and so we're not quite done. So that is the sum of the distance between the observation and the mean squared, then divided by n minus 1. And there's one thing that's left, and that is we need to square root. And if you do that, if you take the square root, what do we get? We get 0.083. We'll round it up to 0.084. It's actually 0.0836. Okay, and so that's how to go through and do it by hand. It's a lot of work. You've got to go through and take observation minus mean, then square, then add, then divide, then square root. Okay, if you kind of take a look back at our formula, you can see all that stuff. You've got to do observation minus mean, then square, add them all up, then divide, then square root. That's what we just went through and did. It's a lot easier to go through and just use StatCrunch to do it. And actually, I discovered a small problem with how we just went through and did this when I went through and checked my work using StatCrunch, and I'll explain what the problem is in just a second. So let's jump back over to StatCrunch, have it spit out the standard deviation for us, and then we can kind of discuss the fact that the result's going to be a little different than what we got. All right, so again, we've got the 12 entries. They're sitting here in a column. Go to stat, go to summary stats, go to columns, select the column, and then you don't need to change anything else. Just hit compute. All right, and then what did we get? We got, there's the mean. We said earlier, 2.66 repeating. And then for the standard deviation, this has 0.074. All right, so in case you've forgotten, what we got is 0.084. So 0.074 versus 0.084, why are they not the same? Well, you think about it just for a second. If this is if you haven't taken a class where you've gone through and did calculations like this, you might not have any idea. But if you've taken a class like this before, then you might have some notion. All right. So anyway, I've given you a chance to think about it for a second here. What's the problem? Well, what did we use for the mean? We used 2.27. We didn't use 2.26 repeating. So I rounded the mean, and by rounding the mean, that caused me to get a different standard deviation. And so anyway, that's just one potential issue. If you go back and do the standard deviation calculations that we did earlier, but you use 2.2666666 forever, you could go through and cut that off at some point, but you'd need to do more decimal points than I did. Otherwise, you're going to get 0.084. As you do more decimal points, you should get closer and closer to 0.074, which is the actual standard deviation. Okay, so rounding, if you round the mean, then that's going to cause a problem with your standard deviation calculation, as we just discovered. All right, so how do we go through and interpret that result that we just got, that 0.074? So we're going to talk about this in a lot more depth in the next video, which is going to be on interpreting the mean and standard deviation. But the standard deviation, if you go through and the number that you get, if you take that number and you subtract it from the mean and add it to the mean, that essentially would be to find one standard deviation each way. Let me try and maybe give you a visual here. So the idea is that if you've got your distribution of data and you go through and you've got, here's X bar, which is our typical value or our center, and we go through and we find the standard deviation and we add a standard deviation. So you go X bar plus S, right? That's going to get you a value. And then we go X bar minus S. All right, so we go one standard deviation, we add a standard deviation to the right, and we subtract a standard deviation to the left. This is going to give us a range of values. All right, the idea is that if the data is unimodal and it is symmetric, then this should be the majority. The majority of the entries, more than half, should lie in this range. And actually, again, we're going to get into this into the next video, but if the data is kind of nicely behaved, it's actually even higher than more than half. I believe it's about 68% of the entries lie within, which we're going to quantify this in the next section, talk about one standard deviation, but the idea of creating a range of values, this is one standard deviation because we added the standard deviation once, and then this is one standard deviation to the right by adding, and one standard deviation to the left by subtracting. The majority of the entries lie within one standard deviation of the center. All right, so that's a way of going through and taking our idea of variation or our idea of spread. If you have a smaller standard deviation, then adding and subtracting it from the mean is going to create a narrower range where where the data has to fall to meet this this standard, that more than half are within that range. If you have a very large standard deviation, then you're going to be adding a very large number and subtracting a very large number from the mean, and so you get different sized ranges depending upon what the standard deviation is. Small standard deviation means a small distance around the mean for the majority of entries to fall. Large standard deviation means a large distance around the mean for the majority of entries to fall. So before we end, actually, there's a couple more things we got to do actually before we end, but we're getting close. What I want to do is I do want to go through and look at the entries. I want to go through and apply that to this problem here. To our gas station. Okay, so how could we go through and find the range of values where the majority of the entries are supposed to lie? All right, so we went through and calculated the standard deviation. We use the stack crunches result, not what we did on this page. Let's use the stack crunch result here. And so we've got the mean. We've got the mean is, let's do 2.266, I guess. And then it's repeated. And then we've got the standard deviation is 0.074. All right, and so what we're going to do is we're going to take the mean and we're going to add a standard deviation to get an upper range for where the majority of the entries are supposed to fall. Actually, let's do the same thing that we did. Let's do a line here. To represent where our entries are. Let's put our mean 2.266. Let's go ahead and do some rounding. Otherwise, it just gets kind of silly. We'll put 2.67. We'll do one more decimal point. Okay, so that's our center. That's our typical value for the distribution. And then our 0.074, what we want to do is we want to add that to get an upper bound for where the majority entries are supposed to lie. All right, so let's break out a calculator. We want to just do 2.267 plus that standard deviation value we got 0.074. So that's going to give us 2.341. All right. And then you want to go through and take 2.267 and you want to subtract a standard deviation. So you're going to get 2.193. All right, so this is X bar plus a standard deviation, X bar minus a standard deviation. Oops, that shouldn't be have a line over it. I don't know why I put the line there. All right, and so now we can go through and take a look here at the data. Does it satisfy it? Actually, didn't check this in advance. I hope it does. So let's see, we got 2.19. Nope, 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 nope. We've got this is in that range, right? 2.2 far. That's 1. Nope. 2.27. That's 2. 2.29. That's 3. 2.17. Nope. 2.29. 4. 2.35. 2.296. So we had 6 out of 12. Barely makes it. That's 50%. So that's half the entries ended up lying within that. That's not great because if you have a nicer distribution, it should be closer to 68%. But we did have the majority, half, do lie within 1 standard deviation of the mean. All right, so that's the significance of that standard deviation number that you get. Whatever it spits out, if you add it and subtract it from the mean, it gives you a range of values, and the majority of your data should lie within that range. The majority of the observations from your data should lie within that range. Okay, so the mean is the center, it's the balancing point, and then the standard deviation gives you a measure for how much spread there is, in your data. Okay. All right, and then one last thing, which I almost forgot about. Literally, I thought this was going to be the last thing, was to go through and calculate this range of values here, is variation. So we're going to use standard deviation significantly more than this, but there is a second measure for spread called the variation. All right, so this is similar to standard deviation. In that it measures the variation, there you go, / spread of the distribution. We are going to use it substantially less often than the standard deviation, but it does exist, and you do see it occasionally. How do you calculate it? It's the standard deviation squared. All right, so if you do that, it's the sum of the observations. Oops, that bar should not be there. The sum of the distance between the observations and the mean squared over n-1. You can see no square root. So if you did not go through and take a square root, take the square root, then you'd end up getting variance instead of standard deviation. And they both are going to have the same qualities, which is that a larger variance goes with more spread out data. A smaller variance goes with more compact data. All right, and so they do both work in the exact same way. The only difference is that the standard deviation, as we discussed, because by taking that square root, we made it so that it has the same units as the mean. The variance is going to have squared units. So we're just going to be finding the distance between an observation and the mean squared and just adding all those up. So we're going to have square units. So to go back to, for whatever reason, I'm sticking with the particulate example. With the particulate example, if you went through and calculated this, you'd have particulates squared. And so taking particulates squared and combining them with the mean would be a kind of a strange thing to do. And so because of that, the variance is going to have some different qualities. Oh, you know what? I forgot actually one more thing I was going to do. I don't know whether this is even worth doing. I think you kind of get the idea. I went through and set things up to go through and use StatCrunch on the other data sets where I could get my hands on them. So let's go through and just do that quickly, just to satisfy me, because I did go through and put in the work to get this ready. All right, so here's a distribution. What this is this is 8th grade scores on exams. Oh, and I totally forgot to give you the context. We did look at this. Which of the graphs did I show you was 8th grade scores? It was this one. Remember this distribution? I forgot to read off of this. This is 8th grade scores on math exams for 46 countries. And we guessed that the mean was 475. What is the actual mean? Well, let's go through and calculate it. All right, so we've got a big collection of data here. What did it say? There was like 64, 64 countries. Hold on. Oh, no, 46. All right, 46 countries. And so to go through and calculate the mean and the standard deviation, we can just go to stat. Once you've got the entries in there, go to stat, summary stats, columns, select the column where the data is. In this case, it's in var2, right? var1 has the name of each place, and then just hit compute. All right, and what did we get? The mean is actually at 466.78, and then we've got the standard deviation is 76. 466, what was it called? Right up 467 and 76. 467 and 76. Let's take a look at this. Yeah, I meant to do this because I thought it was cool. So 466, we guessed it was 475. So 466, we were off by just a little bit, but we're pretty close at 475. And then if you went to that 466 and you added the standard deviation, what was it, 75? You add the standard deviation and subtract it, you'll get a range of values. And that range is going to look something like, if you go through and take 466 and subtract 75, then you're going to be around 400. Let's just kind of put a bar there, right around 400. And if you take 466 and add 75, that's going to be like 530 something. That's going to be close to 550. So it's going to be something roughly like this. And then this distribution does look like the way that it's supposed to, where it looks like about 68% of our entries are here within a standard deviation either way of the center. Okay, so that's one of the things I wanted to show you, is that this graph does, this distribution of data does look like it satisfies the 68%. So that's kind of neat. And then the last one I went through and did is the air temperature. Oh, I remember why I did this one. So this one has San Francisco and Provo. It's got, this is the max temperature for given days. And so there's a lot of data here. You wouldn't want to go to 365 days worth of means and standard deviation using the method that we did by hand. This is exactly the situation where you want to break out a calculator. The thing that's cool about this one, if you go to stat and then summary stats and then hit columns, look at that. You've got you've got three options, but the place where our data is in AirMax SF and AirMax Provo. So to go through and select these, if you click on them, you see you only have one. Oh, actually it did work so that you could do both, but I thought you wanted to hit control to make it select both. I can't get it to unselect Provo. That's weird. Oh, there we go. You do need to click control. All right, so if you've got none of them selected, if you hit AirMax San Francisco and hit control, that allows you to select both. Okay, anyway, once you've got them selected, you can hit compute, and then look at that. It does both the calculations for us at the exact same time. Hey, it looks like there's two pieces of data missing from Provo. That's weird. Anyway, you can see the mean 65, 66.7. And then take a look at that standard deviation, Standard deviation for San Francisco is 8.3. So again, take that mean of 65, add 8.3 and subtract 8.3, and you should get the majority of the data should lie in that range. But to do the same thing for Provo, you've got to add 20.6 to the mean and subtract 20.6. So the range is going to be much larger for Provo because our standard deviation is so much bigger. And so that gives you, again, a little bit more of a reference point for interpretation of the standard deviation. If you took 20.6 and add it to 66, so your range has to go to get to get the majority of the data, you've got to go up to, like, what is that, 87, something like that. Yeah, it looks like about 87.2. You got to go up to 87.2 for the max, and then you've got to go down to, what is that, 46, roughly 46. So you've got to go from 46 to 86 to get the majority of the entries. Whereas for San Francisco, if you take 65 and add 8, you're going to be at 83 or 73. And if you subtract 8, you're going to be, what is that, 57. So from 57 to 73 versus from 46 to 87. That's crazy, right? But that hopefully that really illustrates the difference for you, is how is the difference in size between standard deviations, and helps you to interpret them. Okay. Anyway, so in the next video, we will take a much closer look at standard deviations and play around with that stuff. But that's it for this one. Thank you for watching, and I'll see you next time.